Understanding HPC benchmark performance on Intel Broadwell and Cascade Lake processors. What was the motivation to write the paper?
Well, let's start with good news. In recent years, every year, several new processors relevant for high-performance computing popped up. This is a good situation as it drives competition in terms of price and performance capabilities. However, each of the processors has new features and tuning knobs impacting performance. Further, there's an increasing number of operating system and BIOS settings also impacting performance. Thus, it is no surprise that many benchmarking papers have been published recently. However, the results often differ from paper to paper and are sometimes contradictory. Also, frequently, the numbers cannot be reproduced as important information is not given. Even for the same machine, results differ qualitatively, impairing us to draw any profound conclusions. Therefore, we thought it is time to do a study to identify the major benchmarking challenges on modern processors. The topic is too diverse and complex that we had to stick with two modern Intel architectures and concentrate on data access performance.
Which architectures did you choose? Which tuning knobs and settings did you consider?
We have chosen two Intel processors representing two different families of Intel architectures. A Broadwell processor representing the Haswell-Broadwell family and a Cascade Lake representing the Skylake Cascade Lake line. Both processors support similar clock ranges, host comparable core counts, but differ in the maximum SIMD width they support. Further, the Skylake Cascade Lake line has a completely redesigned Level 3 cache, which also has implications on the Level 2 cache size. This cache size was fixed to 256 KB for a long time on Intel system, but now increased to 1 MB in size. Both systems also differ in the attainable main memory bandwidth, as the number of memory channels has increased from 4 to 6, and also the overall clock speed of the memory was improved. Both systems run the same operating system, and we use the same compiler to compile our benchmark and test codes. Out of the wide range of potential BIOS and operating system settings, we choose a small set of parameters which are known to have performance impact on typical HPC application. Sub-NUMA cluster and cluster on die mode, NUMA balancing, which is also known as page migration for more than 20 years and has already been supported by SGI origin systems. We look at different settings for the transparent huge page features, and last but not least, of course, we investigate the performance impact of clock speed settings for the two frequency domains of Intel processors, core and uncore domain. At this point, let me briefly present the interplay of different BIOS and OS settings when running a streaming kernel, such as a load-only benchmark. Here we choose the Cascade Lake processor at a fixed clock speed of 1.6 GHz. You can see the attainable single-core bandwidth under different settings of the NUMA balancing and transparency huge page parameters for dataset sizes ranging from a few megabyte to a few gigabyte. It is obvious that one of the four combinations of the NUMA balancing and THP settings gets toxic for larger datasets where it delivers almost 50% less performance than the other three settings. The measurements on the right demonstrate the impact of the sub-NUMA clustering setting on the same benchmark. Of course, if you set sub-NUMA clustering to on, this effectively halves the level 3 cache size accessible to a single core, but on the other hand, gives a small performance benefit for main memory access.
Which benchmarks did you carry out on these machines?
Of course, we did use the standard benchmarks such as high-performance conjugate gradient, DGEM, and stream, which represent corner cases of application patterns. In addition, we have implemented our own microkernel or kernel benchmark, which does sparse matrix power times vector representing the performance characteristic of many sparse iterative solvers. However, for microarchitectural analysis, such as effective cache sizes, single-core bandwidths, and multicore scalability of cache levels, we use our own benchmark framework, which directly generates assembly kernels, giving us full control over what we are doing. Our analysis always starts at the single core itself to understand the basic properties of the single core execution. Whenever possible, it is also very useful to compare the results with theoretical predictions derived from machine specifications, which of course represent light speed estimates, upper bounds for the benchmark numbers to be produced. To show what we typically do, let's start with a load-only benchmark, which should determine the single core bandwidths of all cache levels as well as the main memory when reading data. This analysis is also a good opportunity to demonstrate the danger to use black box benchmark framework. The full read benchmark of the LM benchmark suite is designed to do load-only access. The benchmark is easy to install and run, and after a few minutes you get this performance profile using the standard settings, which include -02 compilation level. We find a rather flat performance level, which is in contrast to textbook knowledge, from which we would expect to see 3 prominent performance drops whenever dataset size exceeds one of the 3 cache levels. Further, using information from machine specification, we know that the maximum level 1 load bandwidth is about 200 GB, to be more specific, 128 byte per cycle for each cycle of this Cascade Lake processor. Maybe compiler-generated bad code. Let's try different compiler options. Improving compiler level decreases performance. Well, interesting. Trying other combinations improve performance, but we are still far away from the maximum level 1 cache bandwidth, and we further see strong fluctuations between different runs for some of the versions. We can reduce those fluctuations by forcing the benchmark to use longer runtimes and get more stable measurements. However, in general, you are typically not able to draw any reasonable, well-founded conclusion about the performance levels of the different cache levels from those benchmark results. Let's see what our Liquid Bench framework tells us. Here we achieve almost 90% of the maximum level 1 bandwidth and get a stable performance profile, which we would expect from machine specification and textbook knowledge. Therefore, the message is, don't trust black box tools blindly.
So, now that we know how to get meaningful benchmark results, it is time to have a closer look at these results. The figure shown here shows bandwidth measurements on the y-axis for different dataset sizes, shown on the x-axis. The leftmost part in the figure, on which we'll focus for now, corresponds to measurements for datasets in the L1 cache. An increase in performance can be observed when moving from very small dataset sizes to larger ones. This effect can be attributed to overheads, which have a higher impact when the amount of work the processor is doing is small. The maximum bandwidth that is achieved in the L1 cache is roughly 180 GB per second, which corresponds to about 90% of the theoretical bandwidth. The L1 cache has a capacity of 32 kilobytes, and if the working dataset becomes larger than that, a sharp drop in performance can be observed. At around 80 GB per second, the bandwidth in the L2 cache is less than half of what was achieved in the L1 cache. When it comes to the L2 cache, it is worth pointing out that Intel increased its capacity by a factor of 4 compared to the previous microarchitectures. Instead of 256 kilobytes, Skylake and Cascade Lake architectures feature L2 caches with a size of 1 megabyte. When the dataset becomes larger than the L2 cache, another sharp drop occurs. This time, the impact on bandwidth is even more severe. Going from the L2 to the L3 cache entails a drop in bandwidth by a factor of more than 4, from 80 GB per second in the L2 cache to slightly less than 20 GB in the L3. Interestingly, we don't observe the same sharp drop in bandwidth once the working set becomes larger than the L3 cache size, which is 27.5 megabytes. Instead, we see a much more gradual downturn in bandwidth. Let's have a closer look. So if we zoom in, we can observe a constant bandwidth of around 18 megabytes per second as long as the working set is smaller than the L3 cache capacity. Once the dataset becomes larger than that, bandwidth very slowly converges toward the in-memory bandwidth of around 11 gigabytes per second. If we look at the data in the graph, we find that even for a 100 megabyte dataset, which is almost 4 times as large as the L3 cache, the measured bandwidth is higher than the memory bandwidth. This behavior can be explained by a major change in the cache replacement strategy. Starting with the Skylake microarchitecture, data is placed in only one of the 11 ways of the L3 cache whenever a data access pattern that involves streaming access is detected. To put the impact of this new optimization into context, the following figure compares L3 cache hit rates of different microarchitectures for a load-only access pattern. Hit rates were measured for different dataset sizes using hardware performance counters. To enable a better comparison between the different microarchitectures, which have different L3 cache sizes, the dataset sizes shown on the x-axis are expressed in terms of the L3 cache size of each microarchitecture. The black line represents the Ivy Bridge microarchitecture. We can see that the cache hit rate drops sharply once the dataset becomes larger than the L3 cache size. Broadwell, which is shown in red, shows some improvements compared to Ivy Bridge, with L3 cache hits for datasets up to 2 times the L3 cache size. The most significant improvement, however, is observable for the Cascade Lake microarchitecture shown in blue. Here we can observe hit rates of up to 20% for datasets that are almost 4 times as large as the L3 cache. Even for a dataset 10 times as large as the L3 cache, some cache hits can be observed.
Why do single-core measurements matter? How do they relate to multi-core measurements?
Single-core performance is important because it gives us more insight into the scaling behavior of loops. Here we see an experiment with the stream triad bandwidth benchmark and a working set of 2 gigabytes. This large working set is much bigger than what is recommended in the McAlpin stream benchmark rules because we want to avoid the advanced cache replacement strategy effects that we described before. At a single core on a Broadwell processor with scalar code, we get a reported performance of about 10 gigabytes per second. Now, scaling the number of cores and threads, we see that the performance first scales linearly, but even at 5 cores, we already see an echo of the upcoming bandwidth saturation. At 10 cores, the memory bandwidth has reached about 90% of its saturated value, and then up to 18 cores, nothing much happens anymore. This is the typical pattern of a very strongly memory-bound code, and we see this pattern in many benchmarks and application codes that have a low computational intensity. This is because of the shared resource, the memory interface on the processor. Switching from scalar code to AVX2, we see that the behavior of the benchmark is hardly changed. This is entirely plausible, of course, because SIMD vectorization is an in-core optimization that speeds up the execution of work in the core and the data transfers between the core and the L1 cache, but does not change anything in the cache hierarchy and in the memory interface, so that the main bottleneck, the main memory and the cache hierarchy, is unaffected by SIMD vectorization. Remember that the reported performance of the benchmark in gigabytes per second, as shown in the graph, is not the actual memory bandwidth that is drawn by the code. This is because every write miss to the cache hierarchy causes a write allocate transfer. The benchmark has no way of knowing whether or not write allocate transfers apply, so it has to report the benchmark as seen by the application, which is in this case a factor of 4/3 lower than the actual bandwidth that goes over the memory bus. With x86 processors, we are in the fortunate situation that a special kind of store instruction exists, the non-temporal store, that can bypass the cache hierarchy and thus avoid the write allocate transfer. If we allow the compiler to use non-temporal stores, in this case, the performance goes up by pretty exactly a factor of 4/3. Now the reported performance by the benchmark is exactly the same memory bandwidth that also is used over the memory bus. If we compare the behavior of Cascade Lake and Broadwell, we see that the general pattern is very similar, although on a higher level because of the much higher available memory bandwidth on Cascade Lake.
Do all memory hierarchies saturate?
This is an interesting question. After all, the memory interface is not the only shared resource on the CPU chip. The L3 cache is also shared among all cores, and so the question arises whether or not it poses a similar bandwidth bottleneck. Here we compare the behavior of Broadwell and Cascade Lake with respect to L3 bandwidth using a load-only benchmark with a working set of 2 megabytes per core. This working set ensures that it fits entirely into the L3 cache of Broadwell and into the combined L2, L3 cache hierarchy of Cascade Lake, so it enables us to investigate the scaling behavior of the L3 cache. In case of Broadwell, as shown on the right, we see that going from 1 core to 18 cores, we end up at a final parallel efficiency of about 91%. This is quite good scaling behavior, and it's something that Broadwell shares with all previous generation Intel processors that have a shared segmented L3 cache. However, looking at the data for Cascade Lake, we see that scaling pretty much stops at 14 to 15 cores, and then the bandwidth levels off, and we end up at a final parallel efficiency of 70% only. This leaves us with the conclusion that the L3 cache is not a scalable resource on Cascade Lake processors.
What was the next step after microbenchmarking?
Of course, after microbenchmarking, we investigated into commonly used HPC benchmarks that mimic real-world applications. And here too, we see that the settings of both hardware and software plays a critical role. So let's take, for example, the dgen benchmark, which is commonly used to benchmark the peak performance of a HPC system. With this dgen benchmark, we can get fairly close to the peak performance on modern architectures if we select sufficiently large problem sizes. But on the other hand, small problem sizes do not produce any meaningful results. So one has to be really careful about the settings that we choose when dealing with these kinds of benchmarks. It's also interesting to see how the results we observed in the micro benchmark directly relate to these HPC application benchmarks. For example, the effect of the new L3 cache of Cascade Lake can be directly seen in the results of SPMPV application benchmark. So SPMPV benchmark does a series of matrix vector multiplication where the matrix is stored in sparse matrix format. The SPMPV kernel is at the heart of many applications or algorithms like Chebyshev filter diagonalization, numerical time propagation, and so on. With this benchmark, we could even see the effect of the new L3 cache design of the Intel Cascade Lake. In order to see this, we chose a sparse matrix that fits in L3 cache of Broadwell and L3 plus L2 cache of Cascade Lake. So remember, L3 is like a victim cache for Cascade Lake. In this case, if you do a scaling run, that is plot the performance over increasing number of cores, we can observe the saturation behavior of L3 cache for Cascade Lake. While for Broadwell, this is not the case, similar to the observation made earlier through micro-benchmarking. Even the extended L3 cache size of Cascade Lake can be observed with this benchmark. To observe this, we first choose a matrix which is approximately 1.7 times the entire cache size of both Broadwell and Cascade Lake. If we then observe the memory data traffic of the benchmark using performance counter tools like Liquid, we see that it lies way below the traffic prediction by Roofline model, which clearly indicates that some portion of the matrix and vector are still cached. Similar to the observation made earlier through micro-benchmarking, this effect is higher for Cascade Lake due to its newer cache replacement policy. And consequently, in case of Cascade Lake, the performance is higher than the prediction. This behavior can be observed on Cascade Lake for even larger matrices, extending up to even 3 or 4 times the entire cache size of the Cascade Lake architecture.
SPMV is known to be a basic part of HPCG. Did you investigate HPCG performance as well?
Yes, SPMV and a couple of other similar sparse operations are part of the famous HPCG benchmark, and we did analyze the performance. So basically, the HPCG benchmark solves for Poisson differential equation using a conjugate gradient solver, which is preconditioned using multicore. And similar to SPMV or SPMPV benchmark, the HPCG benchmark is clearly memory bound. And this is also the reason why this benchmark was introduced into top 500 ranking system of HPC clusters, so that it reflects the memory bound behavior of large class of HPC applications. It's also quite interesting to see how even this fairly complicated benchmark code obeys the simple analytical roofline model prediction. So in order to do this roofline analysis, we first isolated the main kernels of HPCG benchmark. And this involves BLAS1 kernels like dot products, Waxby, which calculates linear combination between two vectors, and two sparse operations, the SPMV and multigrid. The multigrid is further composed of two symmetric Gauss-Seidel sweeps and one sparse matrix vector operation. Basically, we can do a Roofline model of all these kernels individually, and then we could add the timing contributions of each kernel to arrive at the final performance estimate of the entire HPCG benchmark. To arrive at the individual predictions using Roofline, the code balance, which is the number of bytes transferred from main memory, plays an important role. So for example, if we see the Waxby kernel as used in HPCG benchmark, it requires to load two double precision elements and store one element back, resulting in a total transfer of 24 bytes per each row of the vector. Once we figure out the code balance, it could be plugged in with the hardware's memory bandwidth that we obtain through microbenchmarking, and together with the number of flops the kernel performs, we can arrive at the final performance estimate. Similar predictions can be done for all the kernels in HPCG benchmark. Obviously, after the performance prediction, one has to relate it with the measurements. So, for example, in case of HPCG, for SPMV kernel, we predicted a performance of 10.43 gigaflops per second on Broadwell. And the maximum attained performance on one socket of Broadwell was almost 88% of the prediction. And one has to remember, the model estimate is a light speed estimate, which means ideally the performance should never be higher than the prediction, which is totally obeyed in this case by the SPMV kernel.
But why is modeling important?
Yes. So the question is, why do we need to model? Because we could just run the benchmark and present the results, right? So there are multiple reasons for modeling. It helps us to gain more insight into the code and its bottlenecks, and also guides us to take the right steps for performance optimizations. But a rather overlooked aspect of modeling is the insight that we gain when a model fails, and to understand why it fails. For example, if we consider the dot product in HPCG code, the performance prediction is approximately 10 gigaflops per second, while the maximum measured performance is sometimes even higher than 11 gigaflops per second. And we have seen that the Roofline model, as we have done here, is a light speed estimate, and therefore the measurement should never be higher than the model. So the initial suspect is some sort of caching behavior. But the measurements were done with the local problem size of 160 cube, which is equivalent to almost 560 megabytes per each vector. And this is even 10 times larger than the entire cache size, ruling out any caching in traditional sense. So we investigated this in detail and found out an interesting phenomenon. This is due to the false assumption that we place into the model, telling that all the threads work on the same kernel at the same time. However, in HPCG code, if we use, for example, one MPI process per thread, there is no synchronization between the dot product and its preceding kernel. Therefore, all the threads need not work on the dot kernel at the same time. And therefore, reuse can happen for data structures that are shared between dot and its preceding kernel. This, along with the desynchronization effect, leads to a higher performance than expected. However, the contribution of dot product to the performance of the entire HPCG benchmark is very minimal. And due to this, we don't see this effect of MPI desynchronization of dot product if we just look into the entire HPCG benchmark picture. So after all, the point is, if we would have blindly made conclusions about the hardware based on the dot kernel, for example, it would be obviously wrong. And therefore, such analysis based on modeling is really important.
I see there are various things that one needs to take into account when benchmarking. Could you summarize them into a take-home message?
These are the main take-home messages from this work. First of all, do not trust black box benchmarks. Always know what to expect and have at least a coarse understanding of what the code does to the hardware. To get there, performance models are an indispensable tool for checking the validity of benchmark results. The latest Intel processors have new cache replacement strategies that require due attention with respect to problem sizes. You might have to choose larger problem sizes than expected to get the actual memory behavior. The same CPUs also have a non-scalable L3 cache, which might impact the performance of application codes in a significant way. Finally, The performance of the well-known HPC benchmark can be thoroughly understood based on the Roofline model on the architectures under investigation. Thank you for your attention.